This is Lab 4, Oscillation of Spring Mass. My name is Bahar Ibrahim. In this lab, we will examine the motion of a mass oscillating on a spring to simulate the physics of extreme sports with ropes. In order to do this, we will create a model in order to compare the model predictions with analyzed data from Tracker. We apply fundamental principles such as the momentum principle, Newton's second law, and the energy principle, as well as concepts such as Hooke's law. The main result of our lab was that the spring mass did indeed satisfy the energy principle. So we know from Newton's second law that F net is equal to the sum of our total forces. In this case, it would be the spring plus the gravitational force. We also know analysis of the energy system will be based on the Earth's spring and mass. And since we have no interactions in our surroundings, we know that delta E would equal 0. Delta E would equal to the kinetic energy, or change in kinetic energy, plus the change in potential of the spring plus the gravitational potential, and that all being 0. So here's an overview of our tracker. We set our origin at the attachment point and set a calibration stick with the given data of 0.7 meters, and our center of mass at the spring mass, at the attachment between the mass and the spring. And here is the oscillations. We use that, we analyzed that, produced the oscillation in the XY direction over time. So here's that. And we save that data in our CSV file. So in order to solve for the spring force and the spring stiffness, we analyzed the period over Tracker, using Tracker, the data from Tracker. So our period, or t, is equal to the time required for one complete oscillation, and that being time in oscillations over the number of oscillations in a given time, and that was 5.32 over 3, and that gave us our result. And to solve for the spring stiffness, we needed to input the period into that formula and got a result. So we know at static equilibrium that the force of gravity will equal to spring force. So at static equilibrium, L was equal to 0.7 meters. So we simply inputted our data and solved for L naught. So going through our code, we simply inputted our basic conditions. The mass of the ball was 0.402, the position we got from Tracker. The initial velocity was 0 since Dr. Greco was initially holding it. Time was 0, start from 0. And here we simply read our CSV data. We used a very small t-step that we were given. G is equal to the 9.8 K spring stiffness we determined. The initial length, or L naught, we determined as well. So then we specify L, which determines the new length by subtracting the spring from the ball position. L hat, we give it the direction. S simply describes the stretch. If it's greater than 0, it's S is used to determine if it is a stretch or a compression of the spring at that instance. So we then sent the total time of the oscillations and set our initial energies. And we know that the force of gravity is only on the y axis, and we know the force of the spring. We know F net, as we already stated. So we solve for the velocity at each instant using Newton's second law, and update the ball dot position. So we continue to do this over the time frame. So we update the length L hat and the spring or compression for each position as we update that. We also update the energy change. So at this point, we can go ahead and plot our energy changes and display our model. And as you can see, the kinetic is the blue, the potential is went a little fast, but the potential of the spring is the red, the gravitational potential is the green, and the total is the yellow, which makes sense because the total would equal 0. So from this graph over here, our model, the blue dot would represent our mass, The blue arrow is the force of the spring. Black is the gravity. A red ball is the observed data from the tracker video. And if you watch carefully, it didn't exactly follow our blue ball, just due to errors in our tracker analysis. We can see a more closely related motion comparison. As you can see, the graphs are quite exact or match well. So the observed data match our model. So the spring mass did satisfy the energy principle. So what does it mean? For your model system, is the energy principle satisfied? As we've already said, yes. Since the yellow line representing the delta E kinetic plus the delta spring potential and the gravitational potential was equal to 0 throughout, from the model we can see that the energy principle was satisfied. As for the second question, using the data you obtained from tracker, make two separate estimates of oscillation from the X position data and from the Y. Compared to. So from the X, I got a result of 1.67 seconds, which was different from the Y. And that's obvious because, well, that is because the X is more related to the pendulum motion, which is different from the Y, which is related to the spring oscillation motion. And each has its own formula of being determined. So that is the reason why. So thank you. This is my lab for